NASA's James Webb Space Telescope, JWST, has only just begun its mission, yet the universe is already proving to be more enigmatic and awe-inspiring than humanity ever imagined. President Biden recently unveiled the first publicly shared image from the JWST, and its capabilities are astounding. Telescopes like the JWST gather much more light than the human eye can perceive, significantly enhancing our ability to observe distant stars. Over the years, various instruments have been developed to further our understanding of space, but none have advanced science like the JWST has. This telescope can essentially peer back in time to the birth of the universe, offering a view unlike any before it. Thanks to the JWST, we now have the clearest image of the City of Lights, which is composed of 18 distinct images, each one captured by a different segment of the telescope's hexagonal mirror. This revolutionary discovery marks a new chapter in space exploration and invites us to explore the implications for the future. The JWST is no ordinary telescope. It is the largest and most powerful space telescope ever created, designed to transform our understanding of the cosmos. Using its advanced technology, the telescope can peer back to when the universe was only 200 million years old, providing a glimpse into the distant past. The JWST can also capture images of the oldest galaxies ever discovered, revealing the first stars shining in the completely dark universe. NASA outlined 4 main objectives for the JWST: to study the first light in the universe, the formation of galaxies in the early universe, the birth of stars and planetary systems, and the origins of life. These objectives are particularly difficult to achieve due to the challenges of obtaining clear space observations. However, the JWST's ability to collect more data than previous telescopes makes it an invaluable tool for scientific discovery. Before the JWST could begin its galactic observations, it underwent a series of critical tests. The Sun Shield, a 5-layered structure designed to protect the telescope's delicate instruments from the sun's heat and light, was deployed during one of the initial tests. Any misalignment or damage to the sun shield could have made it difficult for the telescope to observe distant objects, but fortunately, the test was a success. Next, the telescope's primary mirror, composed of 18 hexagonal segments, needed to be precisely aligned. This process involved carefully deploying the mirror, adjusting the support structure, and unfolding the sun shield. Even the smallest mistake during this process could have resulted in the loss of over $1 billion in potential discoveries. Afterward, each of the telescope's scientific instruments was tested individually to ensure proper functioning. The JWST's precise positioning in space was another critical factor in its success. Its instruments needed to be carefully aligned to ensure that the telescope could observe its intended targets. These efforts required meticulous calibration and alignment with tracking targets to ensure the telescope's success in its scientific mission. The JWST project is a collaboration of nearly 3,000 scientists, engineers, and technicians from 14 countries and 29 U.S. states, making it a truly global endeavor. After passing all its rigorous tests, the JWST officially began its scientific mission in July 2022. NASA confirmed that the telescope was ready to begin its groundbreaking research after all 17 of its scientific instruments had passed comprehensive testing. Like any telescope, the JWST's primary function is to collect light and focus it to allow us to observe distant objects. What sets the JWST apart is its ability to observe infrared light, which is outside the range of human vision. This capability allows the telescope to see objects that are smaller, farther away, and too faint for other telescopes. Because the JWST is in space, it is unaffected by atmospheric distortion, further enhancing its ability to collect accurate data. Its massive 21.3-foot, 6.5-meter, mirror captures light and directs it to the telescope's instruments, which include 4 distinct devices designed to observe different types of light. The primary camera, the near-infrared camera (NIR-CAM), captures stunning images of distant galaxies, nebulae, and other cosmic wonders. The near-infrared spectrograph (NIR-SPEC) provides additional insights into the objects it examines by breaking down light into its constituent colors. The mid-infrared instrument (MIRI) is designed to study the early universe, exoplanets, and our solar system, while the fine guidance sensor/near-infrared imager and slitless spectrograph FGS/NIRIS, assists with precise pointing. These advanced instruments have already produced incredible images and data, sparking excitement and anticipation in the scientific community. For example, the assessment of WASP-96b's atmosphere offered valuable insights into the processes that govern the birth and development of exoplanets. Meanwhile, the JWST's view of Stephan's quintet provided new information about the interactions between galaxies. The first high-quality science image from the JWST was released on July 12, 2022, by NASA Administrator Bill Nelson, Vice President Kamala Harris, and President Joe Biden. This image, captured with just 12.5 hours of observation time, showcased the telescope's extraordinary capabilities and marked the beginning of its exciting mission to unlock the secrets of the universe. The launch of the James Webb Space Telescope, JWST, has sparked reactions from both within the scientific community and beyond, particularly regarding its name. Some have argued for a new name that better reflects the core values of space science, such as objectivity, reason, and inclusivity. Despite these calls, NASA has continued to refer to it as the JWST. These differing opinions highlight the complexity and nuances involved in the creation and launch of a space telescope. The process is so intricate that it illustrates the difficulties in fully utilizing the findings from such a remarkable project. The JWST is a groundbreaking achievement in the field of cosmology, designed to expand our understanding of the universe. Its development spanned over 20 years, involving complex engineering and international collaboration, all aimed at exploring the cosmos in ways previously thought impossible. Launched on December 25, 2021, from French Guiana, the telescope was positioned at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location, where the JWST orbits the Sun alongside Earth, provides a stable environment that helps maintain a steady temperature and an unobstructed view of the universe, which is crucial for its mission to study the faintest and most distant objects in space. One of the JWST's most revolutionary features is its ability to observe the universe in the infrared spectrum. Unlike visible light, infrared light can penetrate clouds of gas and dust that obscure many celestial phenomena. This allows the telescope to explore regions of space that were previously hidden from view, especially the early universe, as light from the first galaxies has been redshifted into the infrared due to the universe's expansion. The JWST's primary mirror, 6.5 meters in diameter and made up of 18 hexagonal segments, is designed to capture this ancient light with exceptional clarity. Each segment is made of beryllium and coated with a thin layer of gold to enhance its ability to reflect infrared light. In its first year of operation, the JWST has already delivered on its promise to revolutionize our understanding of the cosmos. One of its most striking images, known as the Deep Field View, showcases a region of the sky teeming with galaxies, each containing billions of stars. This image, known as the Grandiose Cliffs, offers a glimpse into the universe as it appeared billions of years ago, only a few 100 million years after the Big Bang. The level of detail in these images is astonishing, revealing structures as small as individual star-forming regions in distant galaxies. The JWST has also made significant strides in the study of exoplanets, planets that orbit stars outside our solar system. By analyzing the light that passes through an exoplanet's atmosphere, the telescope can determine its composition, temperature, and even detect potential biosignatures such as water vapor, methane, and oxygen. This capability represents a major advancement in the search for life beyond Earth. One of the first exoplanets studied by the JWST was WASP-96b, a gas giant located about 1,150 light-years away. The telescope's observations revealed the presence of water vapor in the planet's atmosphere, providing valuable insights into the formation and evolution of planetary systems. The telescope's infrared capabilities have also provided new insights into the life cycle of stars. The JWST has captured stunning images of stellar nurseries, regions of space where new stars are born from clouds of gas and dust. These images reveal the complex interactions between young stars and their surrounding environment, including the powerful winds and radiation that shape the development of planetary systems. In the famous Eagle Nebula, the JWST has uncovered the intricate details of the pillars of creation, tall columns of gas and dust that serve as hatching grounds for new stars. The telescope's observations show how these structures are slowly eroded by the intense radiation from nearby massive stars, offering a dynamic view of the ongoing process of star formation. In addition to studying star birth, the JWST has provided new perspectives on the final stages of stellar evolution. Its infrared capabilities have allowed scientists to peer through the thick dust clouds that surround dying stars, revealing the complex structures of planetary nebulae, shells of gas and dust ejected by stars as they exhaust their nuclear fuel. One of the most remarkable examples of this is the Southern Ring Nebula, where the JWST has uncovered intricate details of the nebula structure, including previously hidden companion stars that may have influenced its shape. These observations provide crucial information about the processes governing a star's death and the formation of the elements necessary for life and planets. The JWST's mission is not limited to studying individual objects in the universe. It also aims to tackle some of the most fundamental questions in cosmology. One of these questions is the nature of dark matter and dark energy, which together account for around 95% of the universe's mass and energy content. Although dark matter and dark energy cannot be observed directly, their effects on the universe's structure and evolution can be studied through the observation of galaxies and galaxy clusters. The JWST's ability to observe distant galaxies in the infrared enables it to investigate the distribution of dark matter in the early universe. By studying gravitational lensing, where the gravity of a massive object like a galaxy cluster bends and magnifies the light from background galaxies, the telescope can gather vital data on the role of dark matter in the formation and evolution of cosmic structures. Another area where the JWST is expected to make significant contributions is the study of the first stars and galaxies that formed after the Big Bang. These objects, known as Population 3 stars, are thought to have been made almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. The light from these stars has been traveling through space for over 13 billion years, and by the time it reaches Earth, it has been stretched into the infrared spectrum. The JWST's infrared sensitivity and large mirror make it particularly well suited to detect this faint light, providing direct observations of the earliest stages of star formation in the universe. These observations will help scientists test theories about the formation of the first stars and galaxies and gain a deeper understanding of the origins of the universe itself. NASA's James Webb Space Telescope, JWST, has provided the most profound infrared views of the universe to date. In February 2022, NASA revealed that JWST had captured some of its most iconic images, including a mosaic of 18 scattered bright spots representing the star HD 8446. NASA's Associate Administrator for the Science Mission Directorate, Thomas Zurbuchen, shared on Twitter that these 18 blurry spots would ultimately converge into a single star once the telescope's mirrors were properly aligned, highlighting the telescope's incredible potential for future research. In the weeks that followed, Webb made significant progress. On February 18, NASA released an updated image of HD 8446, showing the star's 18 out-of-focus images arranged in a hexagonal pattern. This allowed scientists to visualize what the final image would look like once the telescope's mirrors were correctly aligned. Once the telescope adjusted, researchers were able to obtain a clearer, more detailed image of the star, thanks to the precise alignment of its mirror segments. During this process, Webb also captured a unique selfie, showing one mirror segment much brighter than the others, illustrating the telescope's extraordinary precision. One of the most remarkable discoveries made by JWST is its examination of the Falcon Cloud, a vast region filled with gas and dust extending into space. Although the Hubble Space Telescope had imaged the structure, it could not reveal its mysteries. Webb's infrared imagery uncovered thousands of protostars, small red spots within the cloud. These are young stars still forming from large clouds of gas and dust. As Derek Ward-Thompson, a professor at the University of Central Lancashire, explained, the densifying gas eventually becomes hot enough to ignite hydrogen, triggering the birth of new stars. JWST's infrared capabilities also revealed a clearer image of the Southern Ring Nebula, also known as the 8-burst nebula. Located around 2,000 light-years from Earth, the nebula is a massive shell of gas and dust ejected by a dying star. The image captured by JWST revealed new details missed by Hubble, including the presence of 2 stars at the center of the nebula instead of 1, with 1 star surrounded by dust. This discovery provides valuable insights into the life cycle of stars and their eventual demise. Perhaps one of the most puzzling discoveries made by JWST was the identification of 6 massive galaxies formed when the universe was only 500 to 700 million years old. These galaxies are significantly more massive than expected, raising questions about the speed at which galaxies can form in the early universe. This finding challenges current theories about galaxy formation and may lead to a rethinking of how we understand the evolution of the cosmos. The naming of the James Webb Space Telescope itself has been a subject of controversy. Although Webb played a key role in NASA's leadership during the Apollo missions, some individuals criticized the decision to name the telescope after him due to his involvement in the Lavender Scare, a period of anti-LGBTQ+ sentiment within the U.S. government. This controversy led to significant debate among space experts and the public, with some feeling that Webb's historical actions should not overshadow the groundbreaking work of the telescope.